this little equation, depending on where E is, and depending on the voltage applied across the membrane that has the channel, the will has a certain amount of current, and you can simply divide this by that, and you get the conductance. Very simple. So conductance is one of the properties that characterizes the channel. Now, channels channels are molecules that can bind other molecules. Okay? And so that describes another property, and that is what other molecules can affect it. So in general, we'll mention that as the pharmacology, refer to that as the pharmacology of the channel. There are many different types of channels, and there are many different molecules that affect them. And some of them are used as pharmaceutical agents. A lot of them are used as pharmaceutical agents, and a lot of them are nasty poisons. So when you guys go to a Japanese restaurant, you ate an egg, this famous fish called fugu fish, pufferfish. You will probably have been informed, or you probably have heard, that it's a dangerous thing to eat, but it's good. So people eat it and pay a lot for it, and maybe because also for the thrill of it. And the reason is that this fish, in its livers and its gonads, it has a huge concentration of a molecule called tetrodotoxin that you may have heard about. So, tetrodotoxin, people abbreviate TPX. It's a very, very powerful toxin that will bind certain sodium channels, so channels that let sodium through and clog them. So if you put this where it was the sodium channel and you added TPX, they consume the sodium channel, this thing will go flat, forever, or for a very long time. And if it opens, it will probably just open for a flicker of a moment, and that's it. So those channels don't conduct anymore, and this has extremely high affinity. It's very hard to wash out. So if you get infected, contaminated, or eat this stuff, your chances of recovery are low. They have to put you on a ventilator because it's blocked all the conduction of the nerves and so on that rely on sodium channels that you will see. And you won't be able to breathe. So in order to make you survive, you will need to be put on a ventilator, and then hopefully this thing will wash out, but it takes a while. So that's the danger. But there's a bunch of other ones. And probably the ones that you are most familiar with are local anesthetics. You go to the dentist, they put you an injection. It's also a sodium channel. Lidocaine and all those derivatives from lidocaine. That's the basic molecule. All those bind also sodium channels, but not the same sodium channels. Okay? So they can bind, or maybe even this. I think it's the same, but they bind it in a different way. So, in fact, we can mention that. So here's your membrane. Let's say this is your sodium channel. This is the inside. This is the outside. PTX binds here. It has binding sites. The channel has binding sites for PTX on the outer mouth of the channel. So it plugs it from the outside. Lidocaine is a non-polar molecule, so it can cross the membrane from, let's say, you put it in the bloodstream or whatever, it will cross and it will bind from the inside. Okay, so, and then you have calcium channels. So ion channels that let only calcium through. Those are very famous because they're involved in arrhythmias and high pressure and so on. So if somebody is taking a high pressure, a drug to lower blood pressure, would probably be most likely be a calcium channel such as
Plando. Plando.
Yeah, but the actual one, that's probably the market name. So anyway, calcium channels are very famous because they're targets for this, and so on. There are many others. And experimentally in research, these things are used because they're very good tools to, for example, get rid of one if you have a cell that has many channels and you want to study the other one. So you want to characterize channels that are not sodium channels. Well, you put TTX in there, or you put iocane in there. And that silences all those sodium channels and you can study them. So very convenient pharmacology. By now we have a huge list, very long list, of many, many molecules that are more or less specific. So when you talk about pharmacology, you always have to talk about specificity for side effects. And some, like prototoxin, is very, very specific. Others, like lidocaine, are not. These guys block a lot of sodium channels. These block a subset of it, and so on. So those two things characterize a channel. The third one that I've been talking about a lot is selectivity. What does selectivity mean? What ion crosses through a certain channel? So you have sodium, potassium, calcium, chloride mostly. But you also have a whole bunch of channels that allow more than one of these channels through. So this TTM sensitive sodium channel, as it's called, lets almost exclusively sodium through, and almost nothing else. Maybe a potassium ion can sneak by, but that's about it. There are calcium channels that are also extremely selective and only let calcium ions. But there are also, so there are, call them specific, but they're also non-specific. And some, for example, let monovalent cations, sodium and potassium through, but not calcium, not chloride. Those are the most common ones. But then there is potassium ions that also let some sodium and so on. So, so that would be one. Potassium ions that let some sodium through, and so on. You have all kinds of overwhelming specificities, and that is one thing that defines it. So that's why I'm talking about sodium channels and potassium channels a lot, because they are very, very selective. And how are they selected? Well, if you look at the structure, you can do that using, people now do that using something that is called X-rays. So you take channels, you make them into a very neat crystal, and you shine X-rays through it. The shadows that the X-rays, that the crystal produces as the X-rays cross, you can look at them, and with very fancy tools, computational tools, you can kind of guess and derive three-dimensional structures from it. But basically, a channel can be seen at a base. So you have binding sites on either side or within, but you also have what is called a selectivity filter. Okay, so this structure here is called the selectivity filter, and all channels have it. More or less selective. And now it's, let's say, a sodium ion feeds in here, it makes it through, and just the potassium ion and make it stuck. So imagine the sodium ion this size, it won't make it to that hole. Yeah. Potassium channel being smaller will probably make it. Okay, so this guy gets stuck, the other one. Now, why would a potassium channel, a sodium channel not let potassium ions through? The sodium is much bigger. And that has to do with how ions are in what state they are in water, in aqueous solution. And that is, they're all surrounded by water. They all are surrounded by water, and as they cross, they need to, and that water can get them stuck. So the actual size is not the atomic size, but this water-shelled ion. This ion covered with a water shell, I don't know how many ions, if it's one molecule, depends on the ion, and that is something that they need to shed before they can cross. And so in these portions in the selectivity filter, there's there are groups that look like the water, like an oxygen sticking out. And so these guys can exchange the sodium, so if the sodium can bind to that, get rid of the water, and then fall. So this also suggests that these ion channels are very peculiar in their shape because they let only one ion through at a time. So that's not not really a characteristic that distinguishes ions, but all channels allow ions to go through in single file. They cannot pass each other. One goes and then the next and then the next. Each step here, there is this exchange of waters and binding of the ion to the walls of the channel that allows for this selectivity to choose, is this ion the right size for me or not? And that's why sometimes the channel that lets large ions through won't let small ions through because of this specific binding in the exact distances that are needed for that.
From a molecular level, if you take a certain drug and put it back in a calcium channel, there's certain drugs I think you're not supposed to take it with calcium or with orange juice. Why is that? Is that would calcium counteract the effects or would it block the?
Yeah, well, these molecules can bind these ions directly sometimes,
Okay.
but also because they're using the same space as an ion is using. So an ion will go through this, as I was describing there, and since this molecule will be using the same space, it's simply a mass action, the result of mass action, like one displaces the other, just like in any chemical reaction. So that's one possibility. The other one is that those substances themselves can be modified by binding to certain molecules or ions themselves. Okay, selectivity. Okay, I'm not going to say any more about selectivity. Just suffice it to say that these channels are quite selective, but some are somewhat less selective. You will rarely see a channel that can let chloride and a cation go through. And that has to do with this, with how these ions go through the selectivity filter. So the cation and an anion are quite different. So they are significantly different. And so the structure at that point really does make a big difference, unless it's a huge channel that lets everything through. And there is one such channel, and that is the channel made in electrical synapses. Remember we talked about electrical synapses very briefly, and what I said, you didn't even barely mention it, right? But these guys are large. Okay, these guys are, the channels formed are large. I'll mention them later in more detail, but they're very large so that they let ATP through, which is a very large molecule, calcium through, chloride, potassium, all kinds of ions, even larger molecules that are dyes, so bigger than ATP, amino acids, not amino acids, but the size of an amino acid for you is even larger. So, large molecules. So that's it, non-specific channel. Okay? Very non-specific channel. All right, and the last property, put it here, but we're going to spend a little time because it goes all day. What is gating? Okay. In the transitions between an open and a closed and an open state, so this is an open state here, happen randomly, but they can also be modified non-random. So if you get a channel at steady state and you look at these transitions, what you will see is that there is a distribution of these openings and closings that looks pretty random. So there will be a lot of one side, not really random, but Gaussian. So you will have a lot of openings of a certain size, many fewer of smaller or larger size, and they will be more or less centered at one value, at one duration. So that describes what's called the mean open time. So they stay open on average a certain time. Okay? So the mean open time will be, I don't know, call it tau O. There's a mean for that, and that characterizes that single channel very nicely. There will be also a mean close time. Okay? And however, this can be pushed by external energy. And the one that is the most familiar to us, it's not really the most, but one very, very, very important is voltage. So voltage across the membrane can be thought of as energy, as a source of energy. It is, right? Produces the movement, so it's a source of energy, produces work, if you like, as an ion moving across, but also in a sense that it can shift the configuration, the structure of this molecule. Okay? And you've heard about this term probably in biochemistry if you're taking it, or even in chemistry, the configuration shift or change in the shape of that molecule that makes it more likely to be open or more likely to be closed. And voltage is a very important one. So voltage is one. And another one is molecules that bind to it, ligands. Ligands is a general term for things, molecules that can bind to it. So EPX and lidocaine, these inhibitors are ligands, but they're blockers. Okay? There are others that can bind maybe on a side or some other part, okay? And this will activate, or that is, push the open state to be more prevalent than the closed state. So they tend to be open more time and longer than other times. So if you can describe a channel in terms of, in these terms, in terms of gating and opening and closing, then one can describe them really as a chemical reaction, right? Between two states, a molecule that transforms from one state to another. So, and moreover, because these transitions, what they do is they let other things happen, like ion channels go through, they act really as a catalyst. So what is in general a catalyst in chemistry? What do we call it? An enzyme. So channels can be thought of as an enzyme. They simply catalyze this reaction, which is movement of an ion from one compartment to another, so they facilitate that reaction. And that's what enzymes do. They speed it up. Because without them, this would happen at a ridiculously low pace. With the channels, it increases quite dramatically, and all of a sudden you have a huge flux of ions to the membrane when this thing is open. So you can describe them as a reaction between two states, rather than binding of something. In the case of gating I'm talking about, so they have rates, right? The rate constant, that would be the rate constant of opening and the rate constant of closing, right? And the equilibrium would be the ratio between these two, right? So you can describe sort of, if you like, a KD, which is the ratio between, or a KA for association, KD for dissociation. So KD would be this, right? And the association constant would be off. Alternatively, you can look at it this way. But just looking at this trace, you can define this by looking at how long does this channel stay in the closed state and how long does it stay in the open state, and define what's called the probability of opening, which is simply the time in the open state divided by the total. So you simply take a stretch here, in the absence of a drug, for example, here, hopefully longer, and you measure this time, you add it to that time, and divide by the total time. It defines in the probability of opening. And this changes, this is what changes as a function of voltage and other things that can happen to a channel, like binding and light. And when we talk about synaptic transmission, we'll see that there are channels that bind neurotransmitters. We're going to write it like this. Okay? And when they do, that promotes the opening of a channel and the flow of an ion. Okay? So the probability of opening then can be described as something that can be voltage dependent or ligand dependent. Okay? So these can change as a function of either one of these. So let's say there is a voltage dependent channel. What you would expect is that at certain voltages the channel is always closed, or mostly closed, and at other voltage mostly open. And if you remember your chemistry, what will describe, so this is voltage, and here we draw this probability of opening for voltage as a function of a voltage dependent channel. What kind of curve would you expect? What is the typical curve in chemistry that you find that relates the state of the enzyme, let's say, to the reaction, something that changes its state? Yeah? Could be parallel, but it's most typically sigmoidal. Exactly. So from a low state where there's not much happening, where the probability that this channel is found in the open state is very, very low, it will rise sigmoidally to a level that is maximally open, so can't open any further. Okay? So this probability then goes from the lowest possible value, which is what? What can be the lowest? 0, obviously. And the largest? When it's always open? 1, right? So this graph here depicts the channel, the state of the channel in terms of how likely it is that you find it open. So you apply a certain voltage across the membrane, now you start looking at the channel. At a certain voltage, the probability that you will find it half open will be exactly at this voltage, whatever that voltage is. If you go beyond, in this case, let's say it's 0, whatever this value is, so let's call it V high, it's going to be mostly 1, right? Very, very close to 1. But if you go below this, let's call it V low, it's going to be mostly 0. So the voltage dependence of a channel, or the gating of a channel as a function of voltage, will typically have this kind of shape. But the same thing is true if you graph this as a function of a ligand concentration. If this channel opens only when it binds ligand, it also will be mostly closed at a certain concentration and mostly open at high concentration. Okay. So for both voltage and ligand, you have the same kind of description. Okay. Now, this can be a little steeper or shallower, and this can move depending on different factors, even for the same channel, but different channels. Also, the curve may be more displaced this way or more displaced that way. Okay. Or they can be steeper in the rest of this graph, but it can be shallow or steep. And these transitions can happen from here to there and back, can happen as a function of yet other things that can bind the channels. Like a toxin, for example, or some other modifier of the state of the channel. Calcium, let's say, ATP, phosphorylation. Okay? Kinase, an enzyme, binds the phosphate group to the channel, and the channel all of a sudden can do something like this, or something like that. Here's a little question for you guys. If you were to record a single channel and you saw this.
If you record.
And then here.
If you record.
So this is closed, and this is the open state. So the record, most of the time the channel doesn't seem to be conducting any current. Not letting the isotope, and then it opens in this kind of pattern. Little flickers, little bursts of activity. If you were to describe it in terms of closed and open states, what kind of reaction would you like? There was an enzyme or something like this that did this. What kind of states do you think this enzyme would be? Could be in. So you drew it like this. I mean, let me put it this way. Would this very simple picture describe this kind of behavior? No, right? Why not?
Because that's showing equal powered and rapid reactions.
Well, they're not exactly equal because these numbers can be different, these rates can be different, but true, it can go one way or back with depending on these kinetic constants, but it can only do either this or that. But this suggests it's doing this or that, but then it's doing something else in between. So let's say we have this closed, that's your simplest possible condition. What else could happen? What else would you add to that whole reaction scheme? Steady state conditions. Nothing else, nothing new is happening from the outside. This is the intrinsic behavior of that channel, of that water.
Can you measure the time intervals of when it's open?
Yes, you could measure these intervals and you can calculate time, open times, and then you have two different mean close times probably, right? Because here it's much longer, these intervals seem to be much longer than between here and there. So that suggests what? Yes. No? Well. So this is closed and this is also closed, right? It looks like two different closed states, doesn't it? So let's say this channel goes to that and then opens. It's like from here to there and then back, right? It's flickering between these two states, and all of a sudden it closes and then stays closed. What would you add to this reaction? 7 sounds like you could have an idea. Yeah, you add another C. So all of a sudden this thing can go to another closed state, let's try that, and this would be just some other it's not exactly open, so let's call it A minus 1. Okay, so it goes back to that. So now you have two closed states. That's exactly it. Very simple. So in fact, this is how channels are described very typically in terms of multiple open and closed states. But there is something else that can happen to channels that is very, very often found. And that's that they go from an open state to another closed state that people call inactivation. An inactive state. So you can call this K1 and this is K, and Ki minus 1. That reaction. Okay. So in this this can also be voltage dependent. These transitions can depend on voltage, as we described in this, right? The probability that a channel will be in the open state, it may be voltage dependent. And this one as well could be voltage dependent. So voltage can move the channel from between different states. Now, this typically goes like this, either here or there. So once the channel inactivates, it remains closed, and it has to go through this other confirmation feed before it can open again. So this reaction is very, very small. I mean, this is really a very tiny error. So channels open, and as the voltage remains high, right? So if voltage is making this transition, the transition backwards will also be dependent on voltage. So here you go from low to high voltage, and you open the channel. This transition happens during a long high voltage pulse. Change the voltage. That's a very key property of voltage, and we call that inactivation. So when you look at these currents, so this is different ways ion channels can work. They go from open to close to inactivated. And what we record, well, this would not be how this would look like. This would be, we draw another kind of scenario for which you could use, this would be the description of. So you would have a channel that goes from closed to open, from closed, and here we're going to draw voltage, so voltage is low, and here voltage goes up, and channels start flickering open, and they can do bursts or whatever, but let me just simplify it like this, and then perhaps a much longer one, and if this stays open, all of a sudden this thing will go down. When the voltage goes down, it remains down until the voltage goes up again. So it opens transiently, and that's a typical property of ion channels that inactivate. They open, they flicker a little bit, and then they close, even if the stimulus, the source of energy that opened them, that produced that transition, that gated them to an open state, we must remain back. Okay. So imagine these molecules are sitting in the membrane, and they're feeling this force produced by the voltage across the membrane. And when that force increases, that changes the conformation and makes them open. But these transitions are random, and the channels just simply, that's the property of all molecules, right? They flicker in different states. The probability that they will go to another state increases, but they can still close or change back. And that's all chemical reactions are like that. Whenever you have an enzyme, it also does that. It can bind to a reagent, a reactant, produce a product, but it will go back to other state, and then bind another one, and so on. So they flicker. No chemical reactions or no enzymes would just stay in one state and not transition back. They're all in this case, if that energy remains high, they can inactivate, meaning the channel goes from the open, the state when the open probability is high,